Imagine AI that can conduct human-level AI research. That kind of AI will help us build superintelligence and hopefully also solve fundamental problems of AI alignment. Our guest today, Lawrence Chen from Metr.org, will share evaluation results of frontier AI models from OpenAI and Anthropic, and also will discuss their capabilities of conducting human-level AI research.
So thanks for the introduction. As has been said, my name is Lawrence. I work as a researcher at Metr. Previously, I was a PhD student at Berkeley. I've done a bunch of other stuff, but today I'm talking about my work at Metr. In particular, I'm talking about some of the recent results we have about AI R&D and sort of why that's important, and also what we have left to do. There's probably four parts to this conversation. The first is what does Metr do? The second is why do we care about AI R&D? Like, why do we care about, in particular, like the sort of machine learning research ability of frontier models? I'm going to talk a bit more about the results we have on AI R&D, some of the more preliminary stuff, and I'm going to talk about why it's hard to extrapolate these into future R&D capabilities. So as a start, what and when, why Metr? So Metr stands for Model Evaluations and Threat Research, but really everyone just calls it by Metr. But for our website, we're not, when you don't know what the company does, I think it's good to look at the website. And today I was looking at the website to make sure I actually do understand what we do, and I think I do. But basically, we're a research nonprofit that works on assessing whether or not cutting-edge systems could pose catastrophic risks to society. What does that actually mean? We have a lot of AI systems, what we call Gen AI, or we have, these large language models running around, not even language at this point, these large models running around that are being integrated in people's lives. We're using them for more and more things. They're clearly very, very smart in a bunch of ways, even if they're limited in other ways. And so there's this question of like, what are the risks? And people all talk a lot about the risks of these things. But what Metr's goal is that instead of like having this conversation where one person on one side is like shouting, oh, the AIs are gonna, kill us all or something. The AIs are terrible. We have to shut it all down. And the other side is shouting, on the other hand, like, oh no, we have to keep going because AIs are so impactful. I think it's a lot more important to assess the degree to which these claims are true instead of just arguing in the abstract or like, shouting trying to derive from first principles whether or not these claims are true. So a bit more about our history. We were founded in around mid-2022. Some of our earliest evaluations with companies was on GPT-4 early from late 2022 to early 2023, including the now infamous TaskRabbit example, where we had GPT-4 early lie to a person, where GPT-4 early lied to a TaskRabbitter about how it's a blind person who needed help, and that's why it needed help solving CAPTCHAs. A lot of our more recent efforts, starting from early 2022, have been on what we call general autonomy evaluation. So we've built a suite of tasks where like language models interact as agents with, for example, like, solving particular puzzles or writing particular small programs. And then we're trying to figure out, like, in general, are these models able to act like agents? More recently, from like maybe October or November of last year, we've spent a lot of effort on AI R&D evaluations. So sort of like trying to figure out how close are the machine learning models from replacing existing machine learning engineers. Recently, we got a large grant from TED Audacious. I'm not sure where that fits in, but we did. And currently we're about 20 people, of which I would say around half are researchers. We're still very much trying to figure out exactly, we're still very new in the grand scheme of things, and we are looking to grow. Before, I haven't gotten to what Metr does, but now that I've talked a lot, let's talk about a bit more about what Metr actually does. One way to look at it is by looking at the topic areas. Broadly speaking, there's two main active areas of research, or two main teams. The first is general autonomy evaluations. So this is like how capable are AIs in general of being agents. If I have GPT-4 or I have Claude 3.5 Sonnet interact with the terminal, like what can it do if it's actually trying? Is it actually like, where does it get tripped up, right? And then the other question, as I've talked about a lot, is, and as is the topic of this conversation, is the AR&D evaluations. And here we're in particular asking the question, how far are AIs from like replacing human researchers in terms of research, or at least like substantially augmenting human researchers in research? And finally, there's parts of Metr that does threat modeling. So this is like we have lots and lots of AI agents People make lots of claims about various ways in which the AI agents are dangerous or aren't dangerous. It's important for us to like sit down, try to actually figure out which threat models are realistic and what does it actually take for the models to be dangerous and not dangerous. Another way we can do it is we can chunk it up by like which parts of Meter are more or less public. So another way to chunk this up is we have parts of Meter that work with AI labs to evaluate large language models. We call this frontier. We call this evals execution is what we call it internally. But basically our goal here is to just go like, yep, here is Claude 3.5 Sonnet, here's OpenAI's O1. How good is it? And like, does it actually, what capabilities does it actually have or doesn't have? And like, how is it close to like, the dangerous thresholds that various companies have specified? Another thing we do is there's parts of Meter that are more research focused. So we do more research on large language model evaluations and post-training enhancement. This is in the sense of like, if I take a large language model and I like, I can't train it on like, 50% more data, but suppose I were to fine tune it with a fine tuning API, or I were to like, scaffold it in some sort of agent scaffold, or I were to like just run it for longer. How large an effect does this actually have? And how do we actually bound the performance of the models under this regime? And then of course, we also have some policy consulting with labs and government agencies. This is mainly in terms of the frontier safety policies that various labs are currently trying to implement, but also we do sometimes engage with various government agencies in terms of like, here's sort of what you should do, here's what you shouldn't do. Here's what Meter does. An important question is, why is Meter doing what it's doing? Broadly speaking, the story of AI risk has to go something like this. People make AIs that are dangerous, and then AIs, do something bad, right? It's a very simple two-step story. Why does this happen, right? Like, well, one reason is that it's a mistake. People don't see that danger is coming. People look at the AI systems and they go like, oh, don't worry, it can't do anything. It gets tripped up by these weird logic puzzles. It's gonna be fine. It won't do anything. It can't figure out this weird word puzzle that screws with the tokenization. It's gonna be fine. But in practice, and it turns out, maybe it turns out that the AI systems are not actually safe. They actually have many capabilities that are dangerous. I think another big reason is pressure. So like if you are OpenAI or you're Anthropic or you're one of the labs, you're under a lot of competitive pressure. You have investors, who've given you billions and billions of dollars. You have like employees who might be poached by your companies. You have, you're not sure what the governments are actually going to do in response to your things. It just seems like a very difficult question that you have to answer. You're like in a very difficult position and you might not be able to make decisions that are like in the best interest of yourself or everyone because you're under so much pressure. So to resolve the mistake angle, we can just do the evaluations, we can see the danger, and we can all agree, if the models are dangerous, we should do some very sensible things. If the models are not dangerous, we should actually just take advantage of the models and try to actually make the best use of we can of them. In terms of pressure, evaluations are important because you have to actually agree on standards. If it turns out that everyone agrees that if the model has this, could replace all the AI researchers, then we need to slow down and we need to like not just deploy and replace all the AI researchers and try to, replace the entire economy with your AI agents. That might alleviate the pressure and makes it less of a winner-take-all situation. But this also requires evaluations. And this is sort of where Meter steps in, or the motivation behind Meter. Yeah, so broadly speaking, again, the story of Meter is something like we try to develop threat models for the next-gen systems, we assess the requirements for the threat models, and then we turn this into concrete evaluation thresholds. Well, what does that actually mean, right? So like, there's a bunch of things you actually want from evaluations. And the most important one is that it actually predicts risk. There's a lot of evaluations out there. Like I feel like every week there's like, oh no, there's another evaluations out there. Or like, oh yes, there's another evaluation out there, right? There's the classic big benchmarks like MMLU, GPQA. There's more like specific agent benchmarks, agent bench, MOE bench, SWE bench, etc. And there's just a lot of interest in evaluating large language models, in part because if you are outside of labs, it's one of the few things that you can actually still do without much model access. But the most important question here, like the biggest question, of course, for evaluations is that it's actually relevant to things. And I think this is actually a really, really difficult question. Suppose a model gets 80% on GPQA. That's incredibly impressive. That's better than most of the grad students that they had baseline, that data set. Or, if it's better than human performance on ImageNet. What does this actually mean? So one part is, in practice, we actually don't know what human baselines are, so we don't even know what these numbers mean at all. But even with human baselines, this is actually pretty challenging still because these evaluations don't capture all the things we care about. So I think it's important. Like one of the things you actually do care about a lot for these evaluations is trying to stick to as close as possible to the thing you're actually concerned about instead of trying to make a very cheap proxy. But another important part about about evaluations that's kind of important here is that you have to be able to draw thresholds. You have to be able to say something like, if the model has this level capability, then this is concerning for reason X or Y. You can't just, go like, oh yeah, we're like, the number has been going up, but we can't tell if there's any point at which it's actually dangerous. This is actually really, really hard. This gets back into the economic, but one way to get around this is, if the models are better than humans at X, and X is a capability we're concerned about, then at least we could agree that this is kind of interesting, this is kind of bad, or like, kind of very useful, depending on your perspective. Of course, then this in turn requires diversity, realistic, economically relevant, and also requires like a meaningful interpretation score. Generally, the second and the third often mean that you have to spend a lot of effort doing human baselines. Also, another thing you might want is you can draw a straight line on graphs. I feel like a lot of machine learning has been very skeptical of building complicated models, but we're still okay drawing a line, especially if the line is in a log-log plot, like all the scaling laws are. So one thing you might really, really hope for is you have smooth enough scaling that you can actually just draw this straight line and go like, well, in 2022, the models were 20%. And, in 2024, they're now like 60%. So, predict in 2026, they'll be 80%, or, 90%, or however much, I'm not sure exactly what your X and Y axes look like, but you might be able to extrapolate out into the future, which might make forecasting a lot easier. And also it lets you like, have an actual like buffer between your threshold and your actual thing. Yeah, so you actually do need a threshold, and in order to have, you want a threshold with buffer. In order to have this buffer, you do actually need to like have this sort of relatively smooth scaling, and you also need to have some sort of understanding of like, here's how much we can get in the course of pre-deployment evaluations versus here's what people actually get in deployment, because it's substantially different in practice. It can be substantially different in practice. Yeah, so that's a bit more about what Metr's general big picture view is. Let's get into the actual question, or like the topic of the talk, or let's at least get into why we're doing the topic of the talk. And that's why AI R&D, like why care about machine learning research and development. So as I've alluded to in the past, a lot of Metr's evaluations were general capabilities evaluations. So what we did is we built a lot of tasks that were, that seemed like relative strengths of AI. So it's in the domains of cybersecurity, machine learning, software engineering, or like puzzle solving or generic research. So like general capabilities that it seems like people are using AIs for in the near term. And then we, built a bunch of tasks of different difficulties. We got gathered somewhere in the order of a few hundred human baselines. And then we had the humans look at, humans actually perform these tasks, which let us sort them into buckets. And then, it turned out I think it was not as good as we thought it was. We thought it would be more uniform, but it's still kind of okay. We still have some diversity. So this task suite has a bunch of, it's really, really diverse. So we have tasks like symbolic regression, which is here's a set of inputs and output, and then you as the model or you as the human try to figure out what the rule is that generates the outputs given the inputs. We have like, other tasks. We have avoiding shutdown. We have file recovery, which is extracting files from disk, giving some node structure, which could be arbitrarily complicated. And then we also have some tasks like the OxDNA stuff, which is more related to particular like niche computing subskills, like working with chemistry data sets, biology data sets, and so forth. Here we do have some preliminary results. Apology ahead of time, because Anthropic released a new model as of like a week ago, and they called it Claude Sonnet 3.5. And it's exact same as the previous one. So a lot of my figures have this random model jammed in with this like, last minute insert a name, because we have this new model, and man, I really wish they named it something that was actually different. But yeah, so broadly speaking, we can given this human baselines and given these tasks, we can run the models with different agent scaffolds on these tasks, and we can compare the performance of models with humans. So we can get, for example, that GPT-4o is somewhere like, the score that GPT-4o achieves on this benchmark is comparable to what a human would get, and if you gave the humans about an hour, and then like, Claude Sonnet, or like half an hour for GPT-4o, and then Claude Sonnet is a bit better, and then the more recent Claude Sonnet, the one that was released in late October, that one is even better. It's closer to an hour than the previous one. And you get results like this, right? So again, like I've said, we've done a lot of human baselines with 44 humans and a bunch of tasks per environment. There's a lot of facts about the humans that we can talk about. We can talk about where we got the human baselines from. We can talk about where the experience is, how experienced these baselines are. But really, the problem I have, and the problem like Metr had in general for this benchmark, is it's not clear what the threat relevance is, and it's not clear what it actually is measuring. Yes, the models are capable. We can see that clearly that the models over time, as we go from left to right, they're clearly getting better. But it's not obvious what this means, right? Like it's not obvious what it means to score about as good as a 1 hour human, given the benchmark is sort of, not exactly doesn't actually get full coverage of any particular task and isn't specifically relevant to a particular domain. Though the tasks are like somewhat interesting, somewhat novel, somewhat require problem solving. It's not clear what exactly that it's measuring. And an important other problem is there's lots and lots of benchmarks in the area. So like back when we were doing the GPT-4 early evaluations, there was not any benchmarks in the area. Agent evaluations were completely unexplored. But in the 2 years since, we've really seen a lot of benchmarks. I've mentioned a bunch of them, like MLE bench, SWE bench, agent bench, SciBench. I don't know. There's probably just like take your favorite word, add bench afterwards. There's like 50% chance there's a benchmark called that in the release in the last 2 years. And so you kind of want to differentiate yourself, and you want to pick a different area that's like more specific to a particular threat model or more specific to a particular thing. And that's what Metr has done. Of course, now there's a natural question. Why this, maybe one of the big questions of the talk is why care about AI research development? And basically, there's a sense in which this is really obvious, right? So like if you look at all the companies, what is the thing that makes Anthropic or like what's the thing that makes OpenAI worth $157 billion or Anthropic worth, I don't know what their current evaluation is on the recent funding round or the recent tender offer round or something. But why is it worth an order of tens of billions of dollars? And the answer is they have the ability to do AI R&D. They can develop AI systems that are much, much more better than than what other people have, or at least that's what they claim, and that's what some empirical results seem to bear out. And the really high, and so this kind of goes like, yep, there's a lot of returns on investment. Clearly, the markets believe this. And extremely fast progress does mean, though, that it's hard to understand and direct it, right? So if the AIs go from like, if R&D lets you go from a system doesn't really work to a system works really, really great over the course of 3 months, there's like no way anyone outside the company will really have much of a say in what happens to that system. And this leads to the next point, which is there's the extreme concentration of power, right? So like right now, if you are Anthropic, if you are OpenAI, there's a sense in which you need a high degree of employee or societal buy-in. So for example, when OpenAI, did some things that were not to the approval of many of the employees, maybe like 20% of the like maybe 30% of the safety concerned employees just up and left for Anthropic. They just like literally just quit and join Anthropic. And this puts a check on sort of like what you can and can't do as the leader of a lab, right? So you can't actually act against employee things. And also similarly, because historically, because companies don't move that fast, there might be like societal restrictions, there might be like time for reactions, there might be time for the market to react. If you were like more of a singleton, if you didn't require your employee buy-in, if you didn't need like society to give you lots of resources to do AR&D, instead you're entirely more like a monolith that was more entirely like separate by itself, or like that only require particular hardware things. This means you get a lot more concentration of power. So on one hand, it's great if you are Sam Altman and you can actually take over the universe or something. That would be great from your perspective. From my perspective, as someone who is not on top of one of the labs, I would not like to see extreme concentration of power. I would prefer it if there was like more societal buy-in to all the things. But also, right, there's also proliferation risks, which is if right now you have an AI system, yes, the AI system, being stolen by China or like, being leaked to a competitor is very, very bad. But there's a limit to how bad it is because you still contain the key part of your company that's worth a lot, which is the R&D part. But if you lose your AI and your AI is the part that does R&D, then yes, security becomes substantially more important because you can just lose the company when you lose the AI. Finally, there's kind of a mundane reason, right? Like the labs have, in response to a lot of government pressure or in response to a lot of like societal outcry, the labs have started to write things that we broadly call frontier safety policies. This is saying like, oh, we're going to evaluate our models for like X and Y and Z. And then if we see like X, we're going to do, A. And then if we see Y, we're going to do B and so forth. So it mitigates a bunch of they create a bunch of if-then policies. And a lot of their if-then policies relate to AI R&D, or at least are tangentially related to AI R&D. So of course it's important to know should the labs are the labs actually holding themselves to the frontier safety policies, or like should the frontier safety policies be triggered? Like another reason, which is more that AR&D is generally neglected by standard national security people, or like by a lot of other people, in favor of like traditional threat models from humans, like cybersecurity, persuasion, or like bioweapons or nuclear development, which is one of the biggest topics that people are concerned about. There are lots of benchmarks in the area, right? For example, there is SweBench verified, which is a recent benchmark from OpenAI that was the subset of SweBench, which is basically consists of GitHub problems, GitHub issues, and then solutions GitHub issues with unit tests. There's MOE Bench, also released by OpenAI in the near term. There's ArcAGI, there's SciBench. So there are a few other benchmarks in the area. But broadly speaking, the main issue with a lot of these benchmarks is that they don't really get into they don't really have very high ceiling. If we go back to the threat model, if we think about what it actually takes for this, it's not the case that being able to resolve GitHub issues. It's not the case that being able to solve Kaggle problems kind of okay. That's not what actually makes an OpenAI like research scientist an impressive research scientist, right? Like its ability to solve new research problems, its ability to work consistently over long time periods, its ability to work with other humans, and so forth. And then, of course, there's also the problem, which is there's no human baselines for basically any of these, in part because it's incredibly expensive to hire machine learning engineers to do these baselines. As a result, it's not clear how representative these tasks are of the tasks that we're actually concerned about. Having talked a bit more about why we might care about R&D, or like why Metr in particular should be doing R&D, let me talk a bit more about the results we have. What we have now in a paper that we're really hoping to release really soon, we have about 7 open-ended evaluation. We currently have in the paper, there's 7 open-ended evaluation environments. We have more that we're currently working on, but we're less certain about. We'd have fewer human baselines, and so aren't really focused on. So 2 examples are, what we're calling a restricted architecture mass language model. Let's build a language model that, doesn't have division or exponentiation. So, cannot implement a transformer that still nonetheless is really good at text modeling. So this is indeed a novel like machine learning engineering problem. It's kind of artificial, but it does require like impressive problem solving. And it is a thing that seems quite challenging even for humans. Other tasks that are more low level. So for example, optimize a kernel, which is here's a function I want you to implement in Torch. And, we have a Torch implementation. It's really, really slow. How can you like implement it in lower level primitives, for example, in Triton, to get it to be a lot faster? All 7 of them are an optimization or prediction problem continuous scoring. We have 0, which is here's a standard starting solution. For example, here's a PyTorch naive implementation that takes like 3 minutes to run or something. We normalize the scores so that a strong human reference solution that we come up with, that gets a 1. And broadly speaking, we're trying kind of hard to get the ceiling to be high for a lot of these tasks, but it turns out this is still kind of hard. So, yes, we have a bunch of tasks that seem quite challenging. For example, the previously mentioned restricted mass language model task, but there's also just other tasks like here's GPT-2. Can you reinforce it, learn it to like be a good chatbot? And it's not clear how high the ceiling is on this one. So, even then we're trying to have a low floor. We're trying to have a high ceiling. We're trying to have it be novel. We're trying to have it be not non-ambiguous. But even then, I feel like some of our work, still work in progress. We still gotta work a bit more. So having talked a bit more about what the different environments and also why maybe you shouldn't believe the results, let's talk a bit more about the results. So the headline result is most of our evaluations are done with Claude 3.5 Sonnet. So this is the June version because the new version just came out and the results aren't confirmed yet. Basically, if we take Claude 3.5 Sonnet, and if what you do is you take 16 instances of this and run this for 30 minutes each, so this adds up to about 8 hours of total effort, you'll find that it actually is able to make non-zero progress on 6 out of 7 of the tasks. And in fact, it's able to do quite well, or like somewhat comparable to human baselines on at least one of them, the Triton kernel task. Of course, there's a question of like, why did you do this, weird sample 16 times, pick the best one and give each one only 30 minutes problem? And the answer to that is that it turns out that if you read the transcripts, 3.5 Sonnet has this problem where it tries to immediately solve each task. And then if it doesn't solve it in the first like 3 attempts, it just sort of flounders around and does nothing. So here we can look at the progress on AI R&D tasks over the course of time. Down in the bottom in this like orangish line, we have Claude 3.5 Sonnet. So you can see, there is some performance. It gets like non-zero performance. And then afterwards, though, it just sort of immediately plateaus. It does not actually benefit from having more than 30 minutes or an hour, or especially not having more than 2 hours to do a task. While if you look at human performance, humans basically can't do the task unless unless you give them like at least 30 to 40 minutes. If you give it 8 hours, which is the length of our baseline runs, you can see that they actually do score comparably to what the reference solution gets. At least the 50 percentile human or like the 80 percentile human, they kind of do comparable to what the baselines do. We have our new results with Claude 3.5 Sonnet new. Again, what a great name. This model is indeed much more capable than the old one. The results are more tentative, and broadly speaking, we can see the same trend though, which is the models try to solve the task very, very early. But however, they sort of start plateauing after a period of time. There's lots and lots of ways we can look at this result. Really, really lots of ways we can see this result. Here's another way to look at this result, which is suppose you have 8 hours total of runtime. How do you chunk it up so that the models get best performance? And it turns out the thing you actually want is you want lots and lots of samples. That's one of the things. Another important result I think we have is that scaffolding elicitation really does matter a lot. So this is the sense in which like we put in some amount of effort and the model performs a lot better. So Sonnet, it turns out, works really well out of the box and works really well with baseline agents. And it's hard to improve with additional agents or a lot of additional structures substantially. O1 preview turns out it turned out we can improve the performance substantially over the course of 2 days. So this was literally, we got the model on like Monday, and then on Wednesday we had an agent that was doing much, much, much better. This was the thing we discovered through qualitative analysis. And the reason for this was basically O1 doesn't actually seem to be a good agent by itself. It seems to be really, really stuck in a particular structure of like one step answering the question, probably because of how it was reinforcement learning trained. Of course, the actual training procedures, the actual details of this are not public. And to be honest, though, I think another important result is you really have to read these transcripts. Going back a bit, so Claude 3.5 Sonnet is internally called a good boy or something. It actually just tries to do the task most of the time. O1 Preview really, really tries to game the task. And this is a part of why we don't have the results. We don't like put the results so prominently. So for example, this was in the system card. But for example, if you ask the model to try to fine-tune a model or like make a fine-tuning script run faster, what the model does is it trains a model, caches the model somewhere, and then it submits a script, which what the script does is it copies the model weights into this new initialized model, and then does a tiny amount of modification to the weight. So it looks like, oh, I trained a new model. In particular, the model literally thinks to itself, by bypassing data preparation, training, and model conversion, we can substantially reduce the runtime of this fine-tuning script. Even though, the instructions explicitly state the fine-tuning has to start from the base model, you can't actually do this. Or like, not that, you can't, you got to train the model. Your script has to train the model, not just cheat and put this model in. So yeah, again, this is part of why our O1 results are more tentative and we sort of don't put them as prominently. We've tried to open source a bunch of our resources. So this is Vivario, which is our evaluation running program, our task standard, our task suite, and some baseline agents. If you wanted to reproduce results and you had a bunch of H100s lying around and you had a lot of time, you could definitely do it on your own. If you wanted to make some baselines, you could also do this. If you have 8 hours of spare time, you could try to do some of our tasks. I think it's quite challenging. So we have some preliminary results, but like the thing you actually want, the thing that machine learning people really, really like, is straight lines on plots, right? Like we really, really want scaling laws, which say as a function of a particular x-axis, whether it's compute, dataset size, or parameter, here's how the performance of the model scales. It turns out it's a bit hard for a bunch of reasons. And the first is we don't have an x-axis anymore, right? So like how big is 3.5 Sonnet? How much compute went in 3.5 Sonnet? I don't know, right? If you look at OpenAI scaling law plots now, the x-axis is completely unlabeled. They just say, oh, this is a log compute, or like this is log a parameter size or something. And we have no idea what the actual size is compared to other models, compared to lab, or in particular compared to models from other labs, or even to like previous generations of OpenAI models. We have some preliminary y-axis, which is sort of like the R&D evaluation talked about before, but this is like a real concern. Like it's pretty hard to know, like what exactly do we care about? And so as a result, without this, like, good or in particular, like, what is the actual metric we care about along these benchmarks? But importantly, I think the third one, which is perhaps as big as the first problem of not having an x-axis, is that post-training elicitation matters a lot. So going back a bit, again, like if you can spend 2 days and you can improve the performance of O1 preview from, around 10 minutes of human performance to over 30 minutes of human performance, what's to say that someone or some genius kid isn't going to come around and go like, oh yeah, I found the one weird trick that makes the models perform 50% better. And I think this is also a serious concern. There's other problems though. So like these are just problems in general of trying to fit scaling laws to any of this. But there's other problems that we have in this area. Oh, there's a typo here. But like It's saturation and correspondence are serious problems. But if you plot the like time to saturation of all the frontier benchmarks, you'll see that they went from like it took 15 years for something like ImageNet or like some other earlier language modeling benchmarks to it takes like 3 years for MMLU, and then now recent benchmarks GPQA, the models reach human performance in the course of like a single year. In addition to this saturation problem, you do have this serious problem, which is the correspondence of any threshold is unclear. So again, like, why do I care that the model is like able to answer like college level multiple choice questions like an MMLU? Like, why do I care if the model can solve Sudoku or like do particular Winograd schemas or there's a ton of stuff inside Big Bench. Like, why do I care about any of this? And yes, you can draw this nice smooth curve. It looks kind of smooth. It's unclear how smooth it actually is. But then again, why do we care? Right? That's a serious problem. And I think one of the answers here is sort of the approach we've been taking, which is we need human baselines to give a comparison of current economic actors. Clearly, we know how much human research engineers are paid, a lot. And we know that they're doing something economically relevant because otherwise they wouldn't be paid so much, and the companies wouldn't be valued at tens to hundreds of billions of dollars. And here, if it turns out that you have a task, which is what humans are currently doing, and also the AI is able to replace the human, and also this task is economically relevant, then like saturation is the exact thing you're concerned about, or it's the exact thing that, is the thing we're trying to measure, right? Like if we have saturation on the thing that's economically relevant, that, where the AIs can replace humans, then like that just means the humans can be replaced. That's like kind of concerning from a bunch of perspectives, kind of desirable from other perspectives, but definitely reflects some sort of very impressive capabilities. Another problem with like all these tasks in general is that it's actually just really hard because if you wanted lots of human baselines for these tasks, it's pretty hard to recruit a lot of these humans. It's like a lot of work to implement these tasks as well, because these are complicated, machine learning tasks with a lot of machine learning. If you do your own research, has a lot of bugs. And the same is true when people try to implement these tasks themselves too. Like not just implementing the solution to these tasks, but implementing tasks which are like automatically scorable. It turns out when we look at people's implementation, there's like 30 or 40% chance there's pretty big bugs. And so this is a big part of why we only have a few tasks. Similarly, we only are able to run the agents for about 100 runs per task. Part of this is each of the tasks, we give them agents like some number of H100s, and we don't have an infinite pile of H100s lying around to give to agents. We have a decent number, but we can't afford to just give any particular agent like 2,000 runs or 10,000 runs or something. And as a result, a lot of the results we believe in are from qualitative analysis, right? So like reading the transcript, going like, why did this model score so well? Oh, wow, it's cheating. Or, why does the model score so well? Oh, why does the model score so poorly? Oh, wow, it misunderstood what the task was. And I think like reading transcripts does give you a really good sense of what the models are like and gives you a sense of, of what the personalities even, what you might say, of these models are. But quantifying these results are really, really hard, right? Like even quantifying human personality is kind of non-trivial as a thing. Quantifying model personality in this area where model psychology is basically non-existent is much, much, much harder, especially when the thing you're concerned about isn't necessarily a property of the model, but sort of an interaction between the model and the environment. Solutions. First solution, we're going to have large language models. One thing we're working on is we're trying to leverage large language models to better evaluate large language model progress. So some of our engineers are currently working, or some of our researchers are currently working on evaluating whether or not how good Claude Sonnet is at evaluating itself. This involves a lot of checking the results that actually come out. But I'm somewhat hopeful that we're going to have more automated scoring, more automated assistance from the language models that do better evaluation in the future. Another answer is we are hiring for research scientists. We are hiring for people. If you're interested in building new tasks, if you're interested in trying to develop the science evaluations, I encourage you to apply. I noticed we're coming up on time, so let's quickly try to go over the takeaways before I take questions. Broadly speaking, what are my takeaways from our results? I think the first one is that it turns out that models can make pretty non-trivial progress on lots of AI R&D tasks. It turns out that Claude Sonnet, if you just give it a small amount of prompting, literally goes and can like implement things that are better than 30 percentile humans. Now, 30 percentile human engineers. Now, granted, 30% of human engineers, something like 15% of the engineers we ran just couldn't score above 0 because machine learning tasks are actually just really hard. So, it's not that impressive in the grand scheme of things. But the fact that, many people were quite shocked that these models can actually implement solutions that function and are much better than the baseline solutions. And this is sort of not super surprising if you use these models as co-development partners or as like research buddies. Because they actually do come with ideas and they are able to like write like really long non-buggy code. And the length of code that's not buggy increases over time. And another important part, though, is that models have really different cost profiles over tasks than humans. So this goes back to the previous results, right? Humans, the human engineers, when given a pretty challenging machine learning and engineering task, they often spend a lot of time trying to figure out what to do. They often spend a lot of time like playing around with solutions that don't work. And then eventually they come up with an approach that works and then scale up that approach. On the other hand, something like Claude Sonnet or even O1, they just try to immediately solve the problem. So they go like, yes, I see this task. Let me implement the code that I think is straightforward. And they might be able to adapt a little bit. They might be able to adapt the code when it runs into bugs, but they're not going to like completely radically rethink their approach like in 2 hours in. Now, how much of this is prompting? That's something we're still trying to settle with internal research, but it definitely seems to be the case that the models are much cheaper if you want a solution that's like kind of okay, but like it's not really possible with current like with reasonable amounts of money in the current scheme to get models to generate solutions that are much better than humans over the course of say 8 hours. Another result I think though is that elicitation really matters, right? So this is the thing I talked about where over the course of 2 days we're able to substantially improve O1 previous performance. It's just really hard to confidently upper bound model capabilities. And that's something I want to work on more in the future, and I hope we make more progress on. And finally, the last thing, which is I can't believe we're harping on this in 2024, because this is something that I feel like all the machine learning people have been saying forever, and yet no one ever does, which is you got to look at your transcripts. You got to actually read your data. Looking at the numbers, the headline numbers, just like doesn't tell you very much a lot of the time. The numbers can often hide important differences. Like, yes, the model does really well, but it does really well by cheating. Or no, the model like does really poorly, but it turns out it's because the task is slightly broken or the model misunderstood it and so forth. And I think this is a thing that surprising people don't do a lot. And so one thing you often observe in these benchmarks is that things are broken. And so I really do think that if you're interested in model evaluations or interacting with models, you just like really see what the models are doing and try to get a sense qualitatively of what the models are doing. And it's super important.